Check it out now, y'all.
nanoHUB-U online instruction.
Welcome back. This is the fourth week in the material science of rechargeable batteries. This week we're going to talk about interfacial reactions, reversible and irreversible. And we're going to start by first talking about the Butler-Volmer relation, which is the core of how a battery works. Now, historically, people have been looking at the interface between a battery particle and the electrolyte as having a charge interface. Where what you do is you take a particle and submerge it or dunk it into an electrolyte, and as a result of that, the ions dissolved in the electrolyte readjust so that those that have, say for example, if you have a positively charged interface, the negative ions will go and be attracted to that interface, while the positive ions will actually be repelled by that potential and try to move away. So as a result of that, then you will have a region at equilibrium that in principle should be rich in anions, and another region in the same regime, in the same area, where it would be deficient of cations. Basically, you will have an effective interfacial charge at the interface, and as a result of that, you will be developing a voltage drop across the interface. Okay, that's the historical idea on how that interface in a battery actually works. In practice, it's really much more complicated than this, because there are a lot of things going on within 10 to 20 nanometers in a battery, but conceptually you can think of a region where you have these ions sitting at the interface trying to hop into the solid phase in an attempt to intercalate and to minimize the free energy. Okay? Now, what actually, mathematically, how we describe this? Well, typically what you do at equilibrium is, well, you start by using a modified form of Poisson's equation, where you have, in this case, phi corresponds to the voltage in the electrolyte, okay, and you have here the effective charge that is dissolved in the electrolyte. In this case, you have a positive and a negative charge, which can be written in terms of a hyperbolic sine function, plus any other charge that in this case could be pinned in the electrolyte. All of those charges are accounted for in the system. You can see this equation is not straightforward to solve. I'm sure you can see that. Even if this Laplacian, you can linearize it. I mean, if you expand it in Cartesian coordinates, you will see that having this nonlinear term really is not helping you solve for the equation. So what people typically do, they just look at this contribution and say, well, if the electrical energy contribution is much smaller than the thermal contribution, then the hyperbolic sine argument can be thought of as a linear term. And if, of course, if you plot the hyperbolic sine, you will find out that to a first approximation in the limit of ZE phi over KBT being much smaller than 1, this whole thing can be approximated as a linear contribution. So you can replace this equation with that equation over here, and you can see this equation can be solved very easily. Okay, and in the absence of, in this case, charges in the system, this will give you an exponential arc response, which is effectively what you saw in the previous slide, where kappa corresponds effectively to the Debye constant. So the inverse of this number is really giving you a measure of the length of that layer where the charge is accumulating or charge is being depleted. Okay, and this really gives you an idea how, if you put more solute in your system, as the C star tells you, that will basically make that distance, again this is 1 over the distance effectively, it'll give you a shorter distance where that charge will accumulate because of the shielding effect that these charges make. Now, this of course corresponds to the simplest description, and a more sophisticated description was done by Geyer, Bettinger and Warren, and here what you have is the concentration. In this case, the solid is on one side and the liquid is on the other one, and what you find is that you can see how the concentration of the different species is such that in this case, for that model, the electrons are piling up on one side of the interface, while the cations are piling up on the other side of the interface. Okay, developing with that, inducing the development of a charge interface that that is going to be driving in this case, the reaction of the system. Okay, and this description really shows you that there's a lot of things that are complex occurring in the system that have to be accounted for as one tries to describe them. This is probably one of the most difficult topics in battery research these days. Why? Because if you think about it, if this reaction doesn't occur, you really don't have a battery. If this reaction is too strong, then you will be able to put a lot of lithium if you want in your battery, but you will be then dealing with the transport limitations of the different phases. So controlling what occurs at the interface is key to maximizing the response of your cell. Okay, now what we want is to have some intellectual measure, some way to abstract that reaction and not have to describe it in these very complex terms. This model, by the way, this numerical description takes days to run. And of course, we want something that as engineers we can take and use in a matter of minutes. Right, so, oh, and by the way, you can see here how this occurs within 2 angstroms for the whole cell. Now, how do we describe this? Well, you can think of the electrode-electrolyte system as the electrode being at the bottom of one well, okay, and the electrolyte being at the other one. And in this case, what you want to do is put lithium ions from one well into the other one, and for that, you have to overcome this energy barrier delta GF. Okay, and at equilibrium, what you have, if the thermal energy is comparable to delta GF, you will have equal number of ions going from the electrolyte into the cathode, as well as the same number of ions basically deintercalating back into the electrolyte. Okay, so that will be the equilibrium situation. And mathematically what we do is we propose the existence of 2 fluxes, a forward flux that is driving the system into the electrode, and a backwards flux that is actually removing those ions, deintercalating it out of the electrode. Okay, now really how easy it is for that reaction to take place will depend on how much stuff we have available here for the reaction to proceed, as well as how much stuff we have in the electrolyte. Clearly, if we don't have any ions in the electrolyte for the reaction to go from right to left, nothing will happen. And similarly, if there are no ions in the electrode, there will be no reaction to proceed in the other direction. So the amount of stuff in both sides will be critical for the transformation to occur. So if we apply a voltage, say an overpotential that drives the system from the electrolyte into the electrode, we expect this energy well to become lower. Okay, and as a result of that, then we would expect then, and given the thermal energy the same on both sides, that the number of hops of ions that occur from the inside of the electrode back into the electrode will be smaller, because relatively this side of the well, the energy barrier will be much higher than from this side that actually may decrease, or it could be the same. Okay, so we would like to account for that. And how many ions will actually manage to make it from the electrolyte to the electrode will really be the difference between the forward flux minus the backward flux. So mathematically, we can just write that in this way by saying the total flux, the total current, if you may, of ions going into the electrode corresponds to the forward ions minus the backward ions. Okay, that's assuming that nothing is trapped at the interface, which could happen. You could have, say, side reactions occurring here that may actually preclude from this reaction to take place, and then we would have to make a correction to that function. Now, we were saying that the reaction will depend on how many spots we have here and how many ions we have there for the reaction to proceed. So mathematically we write that by saying, well, really the forward flux corresponds really to the amount of ions in the electrolyte, and that's why we use this amount CS. Okay, and how many will actually come back will depend on how much material we have on the other side as well. And in this case, Kf corresponds to the forward reaction rate constant, and Kb to the backward reaction rate constant, allowing us in this case to be able to mathematically balance both reactions. Now, at equilibrium, you expect that Jt equals to 0, with that giving you an idea on how to relate Kf and Kb. If you follow that description and you assume that the reaction rate, the forward and backward reaction rate follow Arrhenius type of relationship, then you can say, well, really, the forward reaction rate is really dependent on temperature, where you have this delta GF. Delta GF is the driving force for the transformation. Okay, in this case, there's a forward reaction, the driving force for transformation, and KB is also of that shape and has a backward free energy transformation. If you account for both of them, we can just go and substitute this one here and this one there, and if we do that, we will have then a relationship in terms of the driving forces. Now, which driving force will each of them have? Well, it really depends on how we account for how the overpotential is controlling the system. In this case, we can assume that the Gibbs free energy transformation, there's a natural variable that occurs here because of the discontinuity of the interface, and we have to subtract in the forward direction the drop that occurs as a result of the overpotential that we impose in the forward direction. In the backward direction, we have to add that barrier that we have added as a result of tilting this double well in that direction. So you can see here that's the strength of that driving force, the overpotential, is modulated by Faraday's constant and the charge of the system times some alpha F. In this case, alpha F, you can think of it as the strength of that driving force. How is it that the local material limitations are imposing the internal structure of the interface is making this driving force to be strong or not? Obviously, if alpha is 1, you will get the entire strength of that driving force. And if alpha F is 0, it doesn't matter how hard you tune or you apply a driving force, nothing will go on the other side and it will not see this contribution. Okay, now, if you account for that, you can effectively define an overpotential for the whole thing, okay, and say, well, really, and actually, if you think about it, this really relates, this is effectively the chemical potential of the system because we have a potential associated to the system, okay, plus, in this case, the chemical potential associated to what's occurring in the solid minus the chemical potential what's occurring in the electrolyte. Basically, this term over here accounts for the chemical potential difference between the electrolyte and the electrode, and that difference plus the overpotential is what driving the system in one direction or the other one. Okay, so in this case, you can think of it, you have really two contributions: the overpotential and the chemical potential, the overall overpotential of the system that could drive the system and the system. And now we can take these two contributions, this one substituted in here, this one substituted in there, take these two terms and each of them substituted in here, put it in here, and then if we use the fact that this is a reaction that at equilibrium should be balanced, in other words, if we assume that JT equals 0 when eta is 0, then we will find out a mathematical expression for a reaction to take place. Okay, so if in this case, if we assume that we always have those electrons present at that interface, then we can say that that the limiting rate of intercalation really corresponds to that lithium ion reacting with that spot in the interface and that electron in order to put it into that material. Okay, and of course, in the other direction, that lithium atom is dissociated into a lithium ion and an electron. Okay, and both of them are accounted for. And if you do that, and if you follow the math of the previous slide, what you will find is a reaction that has this form. Okay, where you can see it's really driven by the overpotential itself. Okay, so if eta is greater than 0, this term, the exponential of that term, will be very large, and the exponential of a very small number, a very negative number, will be very small. So in one direction, when eta is very large, this will be effectively 0, and you have exponential dependence in one direction. And if eta is very negative, basically if you go in the opposite direction, then this term will turn off and the other term will dominate, okay, in the opposite direction. Now, what is I naught? I naught corresponds to those terms basically specifying how the concentration at the interface is controlling the reaction. Basically, this prefactor is called an exchange constant. It's not really a constant, it's really a function of the concentration right outside the interface, which is this one, minus the concentration right inside the interface. Basically, what occurs right at the entry door between the electrode and the electrolyte is really controlling how the system behaves. Okay, now you have alpha A and alpha C really modulating modulating the response. There's one constraint in this case for alpha A and alpha C, which is alpha A plus alpha C have to add up to 1. Okay? And really what we're saying is that the overall reaction is balanced as mass is being conserved as the system is proceeding, and at equilibrium the reaction is effectively turned off. Okay? Now these are the simplest interfacial kinetics. What we did here is really an abstract theoretical argument to describe it, and typically what people do to really use this relationship is just they experimentally fit this function and the coefficients associated with that to the experiment at hand. And typically it's very hard to reach very high over potentials. So what people typically do, instead of using the full Butler-Volmer kinetics relationship, what they do is, if you assume that the same rate of intercalation is going to match the rate of the intercalation, you can assume that alpha A equals alpha C equals to 1/2, and again, for cases where we can only apply very small over potentials, that is, for the case where the electrical energy is much smaller than the thermal energy, then what we can do is that we can expand this exponential in Taylor series the same as this one, and if you follow the math and expand this to first order, what you will find is that really you can refer to that relationship as being linearly dependent to the over potential, where still I naught is the same as the previous slide. And here what we find is that well, this linearized description is what people refer to as Tafel Kinetics, and people use this to actually describe what happens in the system. Now, well, we still have that same relationship, so you can see it's still nonlinear with respect of the interfacial composition. Now, how good is Tafel Kinetics with respect to what you would see with respect to using the full Butler-Volmer kinetics? Well, this slide really summarizes it. In this case, I plotted the interfacial current normalized by I naught, so that we only get the voltage dependence as a function of the normalized over potential. And you can see here that as long as it's smaller than 1, in this case you can see that as long as it's smaller than 0.7, I have a pretty good fit, a pretty darn good fit of Tafel kinetics with respect to the Butler-Volmer relationship. And what people do is they measure these relationships very close to equilibrium, and by using that they can actually get this I naught, they can get the coefficients that they need to actually fit this relationship to their models. Okay? Now the composition dependent of I naught, it's important, and actually it could be critical to specifying the performance of your cell. And you can really think that this interfacial kinetics is specifying the instantaneous power of your cell. Why? Because it's really telling you how much charge is being taken from the electrolyte and put into the particle. Okay, or put into the cathode material, put into the anode material. How much of that charge is actually being used really is telling you how much charge you have actually used that you move around your circuit and put into your battery. Okay, from one side of the battery to the other one. So now how does that depend with composition? Well, if I try to integrate that charge, it's really telling me that at the very beginning, if I start, say, for a composition close to 0, I get a very large amount of current, okay, and as the discharge proceeds, that interfacial current is going to reach its peak, about 50% of the charge, and then it's going to come down. That has very important implications on the design of a cell, because it means that at the beginning of the discharge or recharge, okay, the amount of current that you can intercalate is not going to be as large as you will have halfway through. Why? Because halfway through, really the product of the composition of the interface to the 1/2 times the composition of what occurs inside the interface to the 1/2 really gives you the maximum value right at the middle. Okay, it's really a combination of how many vacancies you have available to cross the threshold of the interface versus how many of them are actually being occupied. So if you have too many vacancies available on both sides, there's not a lot of flux to go through, which is what occurs on this side. But if you have too many vacancies being used, then you cannot, not many ions are crossing the threshold, because there's not many spots to basically put atoms, and that's why you have here the loss of instantaneous power. Now, if instead you are somewhere in the middle, that's where you would maximize it, because you will have the amount just right of charge that can cross the threshold and go into one direction to the other one. Now, this is important because the initial instantaneous power that you have at the beginning of the charge can specify how good your cell is. You can think of a power type application, right? It's not the same to have my electric vehicle at this instant when I started, say if you're in a race, as compared to if you're right here at half charge. Okay, that also tells you something about your cell, because I may have a lot of charge in my cell, but I may not have enough charge per unit second at the beginning. You will really have, again, the most amount of charge right in the middle. Okay, and of course, at the end of that discharge, this is basically where you will have to think, well, I really want to discharge my cell. This, of course, is giving you how much charge per unit second we can get out of it. Okay, if I integrate this simple expression, which is completely ignoring all the losses as a function of time, then what I will get really is how much charge I'm using. And you can see here how it starts cranking up at the beginning, goes through a maximum at 1/2, and then starts to slow down, and when I'm very close to the end, it starts plateauing. Why? Because I cannot put enough charge into my system. Okay, now this really depends on the nature of the species at both sides of the interface. If instead what occurs on one side depends on something very different, then this relationship will completely change, and you will have to recast it. And of course, here we're thinking of a flat interface. As you know, particles and batteries are not as effectively flat. They're made out of many particles, and we spent actually the entire week, previous week, week 3, we spent it in its entirety describing porous electrodes of this nature. And even if you have perfectly spherical particles, really how much charge you're using depends on how these particles are distributed. So you can think, to a first approximation, that I have a volume V, okay, of mass that I want to put charge in, and in this case I want to impose through a surface A a certain amount of charge. In other words, I want a certain amount of charge per unit time, per unit area that is crossing this interface. Okay, and usually when I make my battery, that occurs in an electron of a thickness Hc. Okay, and I would like to really try to use those relationships that now I have developed as a means to understand how is it that the particle size and the porosity is impacting on the charge rate accumulation. Okay, so if I do that, what you will find, okay, is that, well, in this case, I can, even though I have, as you now know, you have a particle size distribution. It may be Gaussian, it may be perfectly monodisperse, it may be log normal, you may have clusters of some sort, okay, but you can think of a representative particle RP, okay, that actually is really controlling it, and each of these is exposing a certain amount of area per unit volume that I would like to use to accumulate my charge. So the first approximation, the charge per unit area corresponds, per unit second corresponds to this relationship, which from the point of view of the Butler-Volmer relationship, which already has units of charge per unit area, corresponds to this relationship, okay, and I can use that, okay, and if you do that, well, you can say, well, I can multiply the right side of this equation by volume and divide it by volume. It's just a 1, so it shouldn't hurt, okay. In this case, that area, I can take that area to be the area per unit volume, could be the amount of exposed area that cell actually gives you, okay? And if you do that, then you can say, well, actually, we know what that is. We actually quantify that. We derive a relationship for that. That is the quantity that we define as little a, okay? If you remember, that goes as 3 times 1 minus epsilon divided by Rp, okay? And that really gives you a measure on how much charge you're putting there. Okay, and well, if we do that, we can actually relate that to the area of the system. Okay, and if we do that, you will find then that the total charge being accumulated by the system is proportional really to the thickness of the cell. Okay, times, in this case, the amount of reactive area times the Butler-Volmer relationship. If you do that, then really you have here a measure on how much charge a porous electrode will give you, and it's all really dependent on the amount of area A. Now, I can take this relationship dq dt, okay, and try to relate it to what I already have, okay, to my Butler-Volmer relationship, right? I can write it like this now, okay, and I can go and substitute every single thing I know about it. I know the Butler-Volmer relationship. I know my equation for the amount of area per unit volume, and I know my thickness of my electrode, so I can go and substitute all of that, okay, and this gives me a much more sophisticated relationship, really telling me that for a reaction-limited electrode where that is porous, where I can ignore ohmic losses, okay, really the amount of charge that I can put in it, the power density, the charge rate, is going to be determined really by how porous my system is, okay, how thick my electrode is, okay, the thicker the better in this case, okay, how small my particle is. And notice that here I have a 1 over RP, okay, and it tells me that the smaller the particle size, the more charge I can put per unit volume. And if you think about that, that makes a lot of sense, that the more area I have per unit volume, I should be able to have more instantaneous power. Again, you can think of this Q dot, if I multiply by the voltage, it's really giving me how much instantaneous power the system is giving me. So however, it shouldn't be a surprise that this instantaneous current is really state of charge dependent as a result of these two contributions, okay? And that charge dependent, it's also a function of those microstructural parameters. As we have seen before, the thicker the electrode, the more charge we will get, okay? But also, the smaller the particle size, the greater the instantaneous current, okay? And I do want to emphasize here that this description does not account at all for the porosity, that is the ohmic losses. So if you have this, you would still have to subtract those contributions out of the system. Okay, but, well, we already learned how to do that. So the charge rate of porosity in this case has this form, okay, and now we can rewrite the capacity ratio to have this shape, okay. Remember we wrote it this way. Now we can go and instead of using QC over QA, we can say QC dot over QA dot, and by doing that, what we will find, okay, is that now we can relate some instantaneous capacity ratio that is telling me the rate at which charge is being unbalanced out of the system, okay. We can relate that directly to the Butler-Volmer relationship, basically 1 for the cathode and 1 for the anode, and if you do that, you can find that for a kinetically limited system, this number is going to be time dependent and is going to effectively depend on the solubility limits and the thickness and particle sizes of each of the individual electrodes. If the solubility limit of the anode is much greater than the cathode, which is what we find experimentally, then we can make assumptions like how much charge we can extract and how much charge we can put in, okay? And that gives us a very, very simple relationship for the capacity ratio as a function of the state of charge. And if you plot that, I think the most interesting point here to see is that really you never really have a capacity ratio of 1, which is the most important one, but except at the very beginning of the charge. Other than that, the capacity ratio keeps coming down and the system becomes more and more unbalanced, leading that to more stuff going on outside in the electrolyte in the system as the discharge continues. You would have to actually have a system where the capacity ratio, where the solubility limit of both phases is the same in order to actually have something that is different from 1. Notice that, again, you never really have something close to 1. And, well, in the next class, we're going to talk about those additional extra reactions that occur as a result of that imbalance. Thank you.